Today we're going to cover 2.1 and 2.2, which is if-then statements, converses, and properties of algebra. If you want to follow along in your textbook, lesson 2.2 starts on page 33. So that's what this first part is going to be, 2.1. Pen wasn't done. 2.1 is page 33. So if you want to follow along in your book, you can. Remember, it follows along with that pretty nicely, so that might be helpful to you. So this chapter is when we start our proof writing. So when we do proofs, it's important that we understand kind of our definition, sentence structure, and just some important things about mathematical statements. So our first special kind of statement is called a conditional statement, or sometimes you'll just see it called a conditional. These are statements that are written in if-then form. That should say then. I'll fix that. So statements that are written in if-then form. In other words, we say if our hypothesis, then our conclusion. Okay, so if, whatever you want your hypothesis to be, then your conclusion, and that's our phrase. We use a little bit of shorthand here, so we're going to use the letter P to represent our hypothesis and the letter Q to represent the conclusion. I believe that comes from some old Latin phrasing. So how this is generally written is if P, then Q. If your hypothesis, then your conclusion. And occasionally you'll also see a shorthand with that, which is, it's in a different color, P arrow Q. You'll see that sometimes. That means if P, then Q. And the arrow is pointing towards Q because it's like P implies Q, which if you notice down here, it can also be written with some other phrasing, like maybe you don't see if and then specifically, maybe it writes implies or only if. So P implies Q, P only if Q, things like that. So don't get stuck on just the if and then. It can be phrased in multiple ways. And occasionally we'll refer to these just as if-then statements. Those are our conditionals. Converse, though, that's a statement that interchanges the hypothesis and conclusion of a conditional statement. So our statement kind of flips around. It turns into if Q, then P. So our statement gets reversed. So let's say we had an original conditional statement. It doesn't have to be mathematical. Something maybe like, if you live in Chesterton, then you live in Indiana. That is an if-then statement. You live in Chesterton is the hypothesis. You live in Indiana is the conclusion. That would be our original conditional statement, and that's a true statement. If you live in Chesterton, then yes. If you live in Chesterton, then yes, you do live in Indiana. But what if we took those phrases and we flipped them around and turned them into the converse? Then that statement would read, if you live in Indiana, then you live in Chesterton. Well, that's not necessarily true. And that's because some true statements have false converses. Some things you can flip them around and they're still correct. Others, you flip them around and they become false. Just because you live in Indiana does not mean you live in Chesterton. Right? We can find what is called a counterexample of that. And a counterexample is a specific case for which an if-then statement is false. So if I say something like, if I live in Indiana, then I live in Chesterton, well, maybe I don't. Maybe I live in Valpo, right? That would be a counterexample. I'm showing that statement is false. And it doesn't have to be false, more than once. If something is shown to be false just once, then it is false. So statements are false if an example can be found where the hypothesis is true, but the conclusion is false. So again, if you live in Indiana, then you live in Chesterton. Sure, maybe that hypothesis is true. Maybe you do live in Indiana, right? But just because you live in Indiana doesn't mean you live in Chesterton. It only takes one counterexample to disprove a statement, right? Maybe instead of living in Chesterton, I live in Valpo, and that would disprove that statement. Biconditionals. If a conditional and its converse are true, then the statement can be written as a biconditional. And what that looks like is our hypothesis P if and only if Q. So our phrasing changes a little bit. It's no longer if this, then that. It becomes if and only if. And that's because a biconditional works in two different ways. It works as a conditional statement, if our hypothesis, then our conclusion, but it also works as the converse, if our conclusion, then our hypothesis. Think of it like your phrase works both forwards and backwards. So instead, we can write if and only if. Some place you'll see this a lot is as definitions. All definitions can be written as biconditionals. So for example, let's say we talked about the definition of congruent segments. We talked about that last chapter. And I believe our phrasing went something like, if segments are congruent, then their lengths are equal or their measures are equivalent or something along those lines. Right? If you have congruent segments, then their lengths are equal. But what if you took that statement and you flipped it around? If the lengths of segments are equal, then those segments are congruent. That still works. That still makes sense. So we can write that definition as a biconditional, which would read, segments are congruent if and only if their lengths are equal. That implies it works both from front to back and from back to front, which is why you'll sometimes see a shorthand for a biconditional, which looks like this, P, and then a backwards and forwards arrow, Q. Again, implying it works in both directions. So let's look at some examples here. It says, underline the hypothesis of the following statements once and the conclusion twice. So our first one here, it says, if the measure of RS equals 1/2 the measure of RT, then S is the midpoint of segment RT. It just wants us to identify our hypothesis and conclusion. So remember, your hypothesis is always after if, conclusion is always after then. So our hypothesis here is just that the measure of RS equals 1/2 the measure of RT. And if that is our hypothesis, then we are concluding that S is the midpoint of segment RT. So don't include the if and don't include the then. Okay, hypothesis, conclusion. This one is phrased slightly differently. Angle 1 is congruent to angle 2 only if the measure of angle 1 equals the measure of angle 2. So here you see slightly different phrasing here, but it could be written another way. If angle 1 is congruent to angle 2, then the measure of angle 1 equals the measure of angle 2, right? Either is fine. In this situation, the hypothesis comes first, conclusion still comes second. So our hypothesis is that angle 1 is congruent to angle 2, and our conclusion is that the measure of angle 1 equals the measure of angle 2. Next example says, determine if the following statement can be written as a biconditional. If so, write it as a biconditional. So we talked above about how statements can be written as biconditionals if they work from hypothesis to conclusion, as well as from conclusion to hypothesis. So if an angle is obtuse, then its measure is between 90 and 180. Well, that makes sense, right? That is our definition of an obtuse angle. So think about if we flipped that around and made it the converse. If an angle has a measure between 90 degrees and 180 degrees, then that angle is obtuse. That is also a true statement. Therefore, yes, this can be written as a biconditional. So I'm going to say yes, and then I'm going to just mention that it's a definition. This is just important for us to realize. So yes, because it is a definition. Okay, and now let's write our phrase here. So what you want to do is grab your hypothesis, grab your conclusion, put if and only if between them. You may need to fix a little bit of wording or phrasing to make it a coherent sentence. Okay, and sometimes there's more than one good way to write it. I trust that we can write a reasonable sentence. So my hypothesis is an angle is obtuse. My conclusion is its measure is between 90 degrees and 180 degrees. So I'm going to grab my hypothesis here. So an angle is obtuse if and only if, and then my conclusion, its measure is between 90 degrees. Oh, I spelled between wrong. Is between 90 degrees and 180 degrees. And that is how we would write a biconditional statement. Okay. Next part says state the converse of each conditional. Is the converse true or false? So we're given some conditional statements written in if-then form. It wants us to flip them around and make them the converse. So remember, our converse is in the form if Q, then P. So if we look at our original statement for part A, if x is greater than 0, then x squared is greater than 0. That's true. If you have a number x greater than 0, like 2, and you take it and you square it, it's still going to be greater than 0. So let's flip that around and see what happens. We're going to take our hypothesis, right, which is x is greater than 0. We're going to take our conclusion, which is x squared is greater than 0, and we're going to flip that statement around, turn it into a converse. So we would say if x squared is greater than 0, then x is greater than 0. Well, let's think, is that true or false? If x squared is greater than 0, is your x value also automatically greater than 0? And I'm going to say no. I can think of several examples that this would not work, so we're going to say this is false. And the reason I'm going to say this is false is because let's say we took a negative number, for instance, like -1, right? If you take -1 squared, that's greater than 0, right? -1 squared is 1. 1 is greater than 0. But -1 is not greater than 0. So this is a false statement. And again, that's just one example. There are many. Technically, what I just did is I wrote a counterexample. So then our next statement is if 6x equals 18, so that's our hypothesis, then x equals 3. That's a true statement. If you divide both sides by 6, you're going to get 3. Let's flip that around. If x equals 3, then 6x equals 18. I'm going to go ahead here and say that that is still true. That could still work. If x equals 3, then sure, 6x could definitely equal 18, because if you plugged 3 in here, right, if you're starting with what your x value is, if you plug 3 in here, 6 times 3 is 18, 18 equals 18. So that one is absolutely true. So how our if-then statements work? Remember, you're starting with this first information, right? That's your conclusion. So if x equals 3, then would 6x equals 18? Yes, because if you plug 3 in, 18 equals 18. And then last part for this video, provide a counterexample to show each statement is false. You may use words or draw a diagram. So then that depends on the situation. Sometimes a written explanation is good. Sometimes a drawing is good, whatever you prefer for that given situation. First one says, if the measure of AB is congruent to the measure of BC, then B is the midpoint of segment AC. Now this actually showed up on your chapter 1 test. And just because we have congruent segments, does that mean the shared point has to be the midpoint? Not necessarily, right? They're connected, but at no point here does it say that A, B, and C are collinear. If A, B, and C were collinear, this would work. And maybe this works sometimes, but it doesn't have to. So what I want you to do, I don't want you to rewrite write the statement is what it is. I want you to show me that the statement is false. Either give me a written explanation or an example. A written explanation, you could state that if B is, if A, B, and C are non-collinear, then B cannot be the midpoint of segment AC. So let's write that. I'll kind of show you both. So we could say if A, B, and C are non-collinear, then B can't be the midpoint. Something along those lines. And I mean, it's telling you that that the segments here do exist, but maybe they all don't exist on, on one segment together. And I'll kind of show you what that would look like. Again, more than one good way to state this. I'm just giving you one option. Okay. And then if you wanted to draw me a diagram, I would look for something maybe like this. Here's one segment. I'll call that one segment AB. And maybe segment BC comes off of it like this in like an L shape. Well, maybe these two segments are congruent, right? Segment AB exists, segment BC exists. But if you were to connect segment AC here, B would not be the midpoint, right? Because technically you could still connect a segment with to A and C, but B would not be the midpoint of it. So that would be a counterexample. Part B, if a line lies in a vertical plane, then the line is vertical. Well, you might think, oh, we have vertical plane, vertical lines, that makes sense. And it could be, right? You could have a situation like this, where maybe you have a vertical plane, right? And you have a vertical line going through it. But remember, your planes extend forever and ever and ever in both directions. Your lines through them do not have to be vertical. And it won't let me erase. There we go. Okay. Maybe you have a horizontal line. Maybe you have a line that has a different slope, right? There's a lot of different possibilities here. So you could maybe, as an explanation, say something like, you could have a vertical plane with that contains a horizontal line. Something like that would work. So there could be a vertical plane that contains a horizontal line. Again, this is just one counterexample. There are several things you could say. If you're ever not sure if you can say it, ask. And we can also do a little drawing here. So if you have your vertical plane, I will pretend that it's hard to, quite visualize, but that we're going to say that's a vertical plane, and we'll call this plane X. Maybe you have a horizontal line like this going through it, right? We'll call this point A and point B. We'll also throw point C on there so our drawing is accurate, right? This has a horizontal line going through it, or contained within it, not going through it. Right, because your plane is going to continue and your line is also going to continue. Right, then in the next video, we're going to get into 2.2.